intended result will be this new conclusion, where B has been rewritten into A. The rules that we are going to use to compute this transformation are inspired from a branch of proof theory called deep inference, and more specifically from a work of Kostyv-Choudhury done in 2013, which is called subformula linking, and which is very close to our idea of drag and drop between two subpropositions. So the main idea is that we are going to rewrite expressions of this form, where we have this interaction connective, represented by the turnstile symbol, and the goal of the rewriting will be to bring together the two occurrences of B. So a first step would be to move the hypothesis under the red disjunction. We can do the same with the red conjunction. And finally, we will transform the blue implication into a red conjunction. And here you see that we have this familiar sequence-like expression on which we can apply a variant of the traditional axiom rule, where we will rewrite it into the truth unit. And the final phase of our procedure will be to eliminate all instances of the truth constant. And you see that we end with the result that we wanted. So yeah, that's it for the rewriting sequence. An important property of our rules, obviously, is that they are correct, logically. And another important property, which we call productivity, is that you can take any two subpropositions in the goal which are located in two different items, and there will always be a well-defined behavior for a drag and drop actions, modulo some conditions on the unifiability of the two propositions. So here we focused on an example of backward proof step, that is a drag and drop between one hypothesis and the conclusion. But there is also a second set of rules, which uses a different interaction connective, and which is used to handle forward proof steps. That is, actions which involve two hypotheses.
Let me now say a few words about what happens with quantifiers. We had already encountered quantifiers in the first example when we used the fact that every human is mortal. And what this example showed is that in some cases the quantifiers can be instantiated through a drag and drop action, especially a blue universal quantifier like here. So internally, a first step is the instantiation of the variable x by the object Socrates, and then a standard use of the implication to end up with the goal, the new goal that Socrates is human. The same thing can happen for existential quantifiers, actually red existential quantifiers. For instance here, simple example, I want to prove there exists an object verifying a property. I happen to have an object T which verifies the property. If I bring the assumption here, it will instantiate the quantifier and solve the goal immediately. But what is more interesting, in some cases the quantifier will not be instantiated, which means, again, we will be able to modify the proposition under a quantifier. Here I will modify the conclusion. You see, I know any object verifying a property P verifies the property R, and if I use this assumption under the quantifier here, the goal that there exists a Y verifying R is rewritten into there exists a goal verifying the property P. And this opens the door for some proof steps which would be difficult to emulate easily in a text-based proof system. And this will be even more apparent when we combine the quantifiers with the equality predicate.
In Actema, equality can be manipulated in two ways. The first way is to prove an equality by the trivial argument of reflexivity. This is performed by a simple double-click on a red item which holds an equality, like so. More interestingly, one can use an equality hypothesis through the familiar mechanism of rewriting. For instance, here, I have this blue item holding that t and u are equal, and so I can drag my item and drop it either in the conclusion on this occurrence of u, which will rewrite it into t, or I can proceed in forward mode and drop the t like so. And this generates a new hypothesis where t has been rewritten into u. One advantage of being in a graphical setting is that it is easy to specify many occurrences to be rewritten through a simple selection mechanism. So here I can click on this button to enter selection mode, and I can select, for example, two occurrences of the u expression, and I also select u in an equality, and now when I do the drag and drop outside of the selection mode, I can do the rewriting on both occurrences of u at the same time. By composing the behavior of drag and drop actions on equalities and quantifiers, one gets for free the ability to rewrite modulo unification. For instance, here I can apply this commutativity property on this expression. In fact, the behavior of drag and drop actions on equalities can be combined not only with quantifiers, but also with any combination of logical connectives. For instance, here, I can combine it with implication, which gives rise to conditional rewriting. So when I drag my conclusion on this expression, f of x, here it will rewrite f of n in the conclusion into g of n, and it will also generate a side condition stating that I should prove that n is different than 0.
Some conclusions to finish. So you saw we have implemented a small prototype called Actema for active mathematics, and you can play with this prototype on the web. This prototype allowed us to get some first impressions, some first feedback, and in general we are quite excited. We think there is a real gain to this technology, at least in some cases. Also, the link with proof theory and especially deep inference was really important, even from a very pragmatic point of view, to help us make the behavior of the system more efficient and more intuitive. Here are some possible directions of future work, so I will leave this on the screen for questions. Basically, there is a lot of work ahead, and especially a lot of implementation work, if we want to have a real theorem prover implementing these ideas. Thank you very much.
Thank you. And once again, ask your questions in the chat if you're online, or raise your hand here if any questions. Oh, we have one.
Thank you, that's a great talk. I want to ask, can you reuse the existing tactic to prove some slightly different theorem?
I answer this one. So we have thought about it. Basically, you have to understand it's really a small prototype, and which was to get an idea of what is happening. It's not meant to be used. Even the question of what are the proofs which are constructed is not really answered, but it's basically to be decided later. We can think of putting an existing theorem prover like Isabelle or Koch or something like that behind it. But even the fact of showing the proof is not, it raises new interesting questions. So basically, maybe you would like a video which is replayed. And then indeed, the question of modifying it is even going one step further. So it's among the questions, interesting questions, which are open, I would say.
Thanks. I imagine that one potential use case is to, for pedagogical reasons, it seems like this would be an engaging way to teach first-order logic. Have you thought about, have you explored using it in the classroom?
Yes, so when we first thought about this, I remember in the car driving and hearing somebody complaining about or saying pupils nowadays don't do enough mathematics, but using high tech it will change. So I don't know if someday we will teach mathematics like that, but obviously I think the first how do you say, there's a group cible, but basically marketing target would be education at some point, yes.
I'm just checking online. There have been a few comments in the chat. I don't know if there's any specific questions that have been asked. I guess one comment was that the issue of replaying seems similar to AGDA, where you construct terms by interaction but lose trace of the end. Maybe there's some lessons to be shared between those two modes of proof creation. Any other comments or questions from online or here?
It's more like a quick comment. I played with the system. It's very fun. I might like to. So I do have a quick feedback that I might want to double click on the assumption or the conclusion when they exactly match.
So yeah, you can do this, of course. We haven't demonstrated it in the talk, but you can just double click on the assumption if it matches the conclusion.
Oh, intuitive user interface if the suggestions from the audience match what you've already implemented.
Yes.
Excellent. So there's a lot of good discussion going on, but I don't think I'll recap it here. Any other comments, questions? If not, let's thank the authors again for this one.